Welcome to this explainer. Today, we're taking a data journey. We're going to dive right into the absolute core of computer science to figure out how structured thinking takes raw, messy data and transforms it into pure, functional magic. We'll be unpacking an entire academic progression, a journey that literally takes us from plain English ideas all the way down into complex C programming. As you'll see, problem solving really is an art form all on its own. So let's kick things off with a bit of a provocative question. What actually matters more? Having blazing fast hardware or just having a really good idea? I mean, we usually assume that if a program is running slow, we just need to go out and buy a faster computer, right? But is that actually true when your data gets massively huge?
Well, this comparison completely blows that assumption out of the water. Computer A is an absolute beast. We're talking 10 billion instructions per second. But it's running a clunky algorithm called insertion sort. Now, computer B, it's literally 1,000 times slower, just 10 million instructions per second. But it's running a highly efficient algorithm called merge sort. If we tell both of them to sort 10 million numbers, computer A chugs along for over 5.5 hours. Computer B, it finishes the whole shebang in under 20 minutes. Seriously, 20 minutes versus 5 hours. The takeaway here is that the algorithm, your core strategy, completely dominates performance as your data grows. Hardware can only do so much.
Which brings us to a really fundamental distinction in computer science, something R.G. Dromey perfectly nailed. An algorithm, that's the pure idea. It is the what to do. A program, on the other hand, is just the specific translation of that idea into a language, like C or Python, so a machine can actually execute it. Think of it like this. You could write the exact same algorithm in 10 different programming languages, and the underlying logic wouldn't change one single bit.
And if you look at the actual academic syllabus for this stuff, it totally reflects that philosophy. Unit I is all about algorithms as a technology. It focuses on flowcharts and fundamental patterns, things like exchanging values or counting. Notice something? There's no code yet. The goal is to intentionally build that conceptual foundation first. It's only later, in Unit 2, that we transition into actual C programming syntax, learning how to express those exact same ideas using variables, loops, and pointers.
So how do we actually tackle these programming challenges without getting overwhelmed? We lean on Dromey's 6-stage method. It's a brilliant framework that walks us systematically through the whole process. First up, we define the problem precisely. Then, we form a model, which basically means choosing the right data structure. Stage 3 is designing the algorithm itself, followed closely by verifying it on paper to make absolutely sure it handles edge cases. Only then, at Stage 5, do we actually sit down and implement it in C. And finally, Stage 6 is testing that compiled code against real data.
Okay, to make all this abstract theory super concrete, I want you to meet our hero for this journey. It's a really simple array of 5 student marks: 42, 78, 55, 91, and 63. We are going to carry these exact 5 numbers with us through every single unit. Why? Because tracking identical data through different processes is honestly the absolute best way to see how simple operations slowly build up into incredibly complex machines.
All right, our very first fundamental building block is literally just exchanging 2 values. Now, on paper, if you want to swap the values of 2 variables, let's call them A and B, you can't just overwrite one with the other, right? You'd lose the data. You need a temporary holding spot. In C, we take this a massive step further by unlocking pointers. Pointers are amazing because they let us pass the actual memory addresses of our variables into a function, which means we can swap the data directly in memory. It's a tiny piece of logic, but trust me, it is absolutely vital.
Now, as we level up into Unit 3, we take those tiny building blocks, the swapping, the counting, the summation, and we start applying them to real named array techniques and factoring methods. We graduate from simply swapping 2 variables to reversing entire arrays, discovering prime factors, and even manipulating matrices. It's like learning basic chords and then finally playing a whole song.
But wait, before we throw our hero array into the blender, we really need to talk about scalability. Because processing steps can explode exponentially as your dataset grows. Just look at these growth rates. If you have an O of n squared algorithm, scaling from just 10 items up to 10,000 items causes the number of computational steps to skyrocket from 100 to 100 million. That's insane. But look at the highly efficient O of log n column. For those same 10,000 items, it only takes about 13 steps. 13! This is exactly why choosing the right mathematical strategy is everything.
Right, getting back to our hero array. Let's do a simple linear scan, which is an O of n operation. If we want to find the maximum value, we just keep a running best so far candidate. Start at 42. Is 78 bigger? Yes. Update our best. Is 55 bigger? Nope. Is 91 bigger?
Yes, update it again. Is 63 bigger? No. And boom, just like that, we found our maximum of 91. It's a super simple iterative refinement.
Okay, pay close attention to this one, because the absolute most crucial array technique we're going to learn is called partitioning. Partitioning is when we pick one specific element, we call it the pivot, and we completely reorganize the entire array around it. Everything smaller than the pivot gets shifted to its left, and everything larger gets shifted to its right. Keep this concept in your back pocket because it's a real game changer for what comes next.
And that sets the stage perfectly for Unit 4. Honestly, this is the climax of the whole academic journey. This is where every single pattern we've traced since the beginning, the exchanging, the counting, the partitioning, finally assembles into complete, incredibly powerful sorting and searching algorithms.
Think about this. We can sort those exact same 5 marks using 5 completely different methods. We could use selection sort to repeatedly hunt down the minimum. We could use exchange or bubble sort to swap adjacent elements until they bubble up. We could insert them one by one, use shell sort for distant gaps, or use quicksort. What this really proves is that the destination is always exactly the same, a neatly sorted array of 42, 55, 63, 78, and 91, only the underlying strategy changes.
Let's actually look at quicksort in action on our hero array. Quicksort simply uses that partitioning trick we just talked about, but it does it recursively. So we partition the array around the last number, 63. The algorithm splits the array, putting 42 and 55 safely on the left and 91 and 78 over on the right. And how does it actually move those numbers around? It uses the exact same fundamental 3-step swapping logic we learned all the way back in Unit I. It's incredible to see everything come full circle like that.
And once that array is finally sorted, that is when we see the absolute superpower of algorithms for searching. If we wanted to find the number 91 in our original unsorted array using a linear search, we had to check 4 different numbers. But on a sorted array, we can use a binary search. By repeatedly having the dataset, checking the middle, and instantly discarding half the remaining numbers, we can zero in on the number 78 in just 2 comparisons. That is that hyper-efficient O of log n growth rate we saw earlier actually coming to life.
But here's the real plot twist. When we move on to text processing, it turns out it's just array processing wearing a different disguise. Seriously, a string of text is simply an array of characters. Padding a line with spaces, that's just our old counting algorithm. Searching for a specific keystroke, that's just a linear search. Deleting a character, that is literally just array shifting. Everything is connected.
So I want to leave you with a final thought to kind of chew on. Think about the device you're watching this on right now. Is the text you're reading on this screen just an array of characters being continuously manipulated, padded, and shifted by the exact fundamental algorithms we just broke down today? Because once you see that underlying structure, you realize this entire digital world is built on these exact same simple, elegant ideas. Thanks so much for joining me on this explainer, and keep questioning how the data all around you is really built.